Get started with today's lecture. Until now, what we have been talking is last chapter was about orbit determination and coordinate transformation, right? Now, with regards to coordinate transformation, do you guys remember what we did? Or sorry, not coordinate transformation. Orbit determination. What is the orbit determination problem? What is the orbit determination problem? Can you define, when you're asked to define a problem, if I ask you a question, what is the orbit determination problem? How are you going to define it?
You're given R, and you find the right ascension and declination.
That's not orbit determination problem.
That's not right.
What is the orbit determination?
Oh, you find R, you find B, you find DR, you find H.
No. How do you define a problem? When you're asked to define a problem, be very specific. Yes. Define the problem. Nobody?
You compute the orbital elements.
Right. So, what is given and what are you trying to compute?
You're given R and B
Right.
vectors.
So that is the orbit determination problem we discussed. Given R and B, right? Was you were given R and B in what frame was this? ECR frame. Okay. And you are required to find
Orbital
orbital element. Okay. It is H or A, E, capOmega, H, E, theta, capOmega, I, and smaOmega. So this is the orbit determination problem, right? And we have looked at how to go about finding this. Now, one of your exercises, untold or unwritten exercises, is you have to figure out the range of these three. Okay? And this one as well. How to figure out this key. So all this, you're going to get two values. You have to figure out how to choose one. Now the reverse is you're given H, A, E, theta, omega, I, and smaOmega. Can you find R and V? Okay. So if you're given these, how do you find R and V? That is one of the problems in your assignments. So step one, and this is not in the textbook, so make sure you at least take a note or go back and review the lecture. It's in the textbook, but it's not exactly this. Okay. The textbook page number is 216 and 217. Now what you can do is, what is this R? How do you express this R?
H over B.
H over mu, H2 square over mu, not h over mu. You have h square over mu divided by
1 plus E cosine.
1 plus e cosine theta. What do you know in this?
You know H. What is H of A? What does that mean? H or A. Oh, H or A. Oh. You
What
know,
do we know?
you know mu, you know H. You know theta. And E. You know everything.
So you know everything. So does that mean you know R? You know this R?
No.
No.
Because it's only reference to my
You
formula.
have to multiply by U.
Right. So what if I write this R as if I write it like this, does this make sense? I'm going to explain this to you. You have this, right? This is your orbit. What is this direction? This is the perigee direction. Let's say this is your R. Okay. This R, what is this? Now, if you have to understand that here, if you express R in terms of the PQW frame, just remember this is an ECI frame. Okay? If you express this in PQW frame, what is the X component or the P component?
Oh, it would be the cosine of the theta.
Cosine of theta, because this is theta, right? So this is the cosine component. This is the sine component. And what is the P component, Q component, and what is the W component? Where is the W direction? Here, so here is your PQW. P, Q, and W. Yes, W is in always the direction of H. So what is the W component?
Oh, Z. Well,
So what is the component?
That's zero.
0, right? It is 0. You see? This is the magnitude, okay? And this is the, so this would be P, this magnitude of this into cosine theta, right? This would be magnitude of this into sine theta, and the component coming out is 0. Okay? Now you have this, right? Now what is velocity? Velocity PQW. Look at this, okay, and tell me what is changing. Look at this.
Theta.
Theta is the only term which is changing. So if I can write the velocity component as mu over h, okay, into minus sine theta e plus cosine theta and 0. Again, velocity will not have a z component. What I have done here is I have just taken the derivative. Derivative of this with respect to
Theta.
theta. So if you look at that, it is h square over mu. You take the derivative of this you take a derivative of this, you take a derivative of this. You're going to get it. Okay?
What if they're next to cosine? Oh, E plus cosine.
Yeah, E plus cosine.
Why you take E plus cosine then? Are you taking the derivative of cosine?
Yeah, you take, it's not just this, it's the whole thing. I'll let you try this. Okay? So here, these are, this is,
This what? ID low plus low half low
minus sin theta E plus this is P, Q, and you want me to do one of them?
Do it for E cosine.
So you have, so let's look at the P components, okay? I'm going to do it here. Right. It will be h square over mu 1 over 1 plus E cosine theta and cosine x. Right? This is the P component.
Why is it times cosine
So it multiplies. This is a vector. X component, Y component, Z component.
But if we know P, how come we didn't use?
No, Q is sine theta.
I have taken this and multiplied by the P.
Never mind. I was looking at the wrong one.
So if you look at this, it is h square over mu. What are you going to get?
You're going to get 1 over E.
Huh? It is 1 plus E cosine theta into minus sine theta. How do you take the derivative of these two? Quotient rule?
Yeah, no,
Are you
it's
taking the derivative of that?
yeah.
What is this velocity? This velocity is nothing but derivative. Right? Velocity is nothing but derivative of this. You understand?
Oh, high minus high, you know.
Plus cosine theta into what are you going to get?
1.
plus
Oh,
You're
yeah.
not going to get 1.
Oh,
You're going to get E sine theta. 1 is 0, right?
oh, yeah.
Then you have 1 plus E cosine theta square.
Wait, God, Sunday, you didn't take the whole, you didn't take the derivative of E. Oh, yes, you did.
E sine theta.
We taking the derivative thing, though.
You have x square over mu. This is
That would be negative sign. Right?
which one? Negative. So
Oh.
A over B is B derivative of A
Okay.
minus
Yeah, okay. Yeah.
minus B derivative of A. You have to suggest something, right? You cannot just say this or this.
No, I'm trying to understand.
It's derivative. It's quotient rule.
Oh,
Or ask. Just ask if you don't understand. It's quotient rule.
is there no particle either? Or cosine theta, particle of 1 to
No, cosine theta is one thing. E over cosine, 1 plus E over cosine is one thing.
Oh, we
So
take
the quotient rule, you take the.
I was taking the derivative of 1 plus 1.
No, we take the derivative of the quotient.
You can
Cosine
either
theta
do the
over 1 plus
you can
E
either do the
cosine
quotient
theta.
rule or you can do the product rule. Either one. So here we are doing the quotient rule. If you do the product rule, it would be this into this.
Yeah, that's too complicated. You don't it's low, you take it to the low, it's high, minus high. Overload easy. I mean, no square, right? That ain't gonna do it though.
Is it PN9?
Well, yeah, yeah, not with it.
If you don't follow, ask or suggest.
Because it's minus. Oh, never mind. Yeah.
You have a square over mu. 1 minus e. So sin theta.
Sin theta. Oh, 1 plus cosine. And then when you multiply it out. I don't see how they get it. 1 over the sin theta. Yeah, that should be plus. Yeah. This should be plus. Because this sign is negative, so it should be plus because it's already minus. Nope.
Okay.
Yeah.
This is plus.
Mm-hmm.
So this is plus.
Yeah.
So you go
They cancel out. Yeah. So you should get 1 over that. Yeah. Yeah, because it's sine, cosine, negative, cosine, negative, root to the lower But I don't see how you wind up getting negative sine. It's low like P high to the root of negative sine. High.
So this is a square over mu. All right, let me come back to this. Okay, let me finish this. I'll explain to you. I'll make sure I explain to you how to get here. Okay. For now, just think about taking the derivative of this and getting there. Okay. Now, what is the relationship between? You're required to find R and B in ECI frame, right? Now, how do you find that?
So now that you
How do you
have.
go from PQW to ECI frame?
Oh, yeah.
Right. So you remember this R. What is this? R PQW to ECI is equal to R
R1 theta.
3.
Yeah, 3 theta. I thought it was. Omega. Oh, it was omega. R1 I and then
R
capital
3.
capital.
Right. Now there is a relationship. I told you this relationship. R
So going from
PQW.
PQW to ECI will always be that matrix, right?
Yes.
Okay.
PQW to ECI. Okay. So this makes sense.
No.
This is a 3 by 3 matrix.
Mm-hmm.
This is a 3 by 1 vector This is a 3 by 1 vector. 3 by 1 vector. 3 by 1 matrix.
Wait, that's three by one.
This is a 3 by 1, right? 3 by 1.
But ECI and PQW is both 3 by 3, right? 3 by
This is
1, right?
3 by 3.
Yeah,
This is
so
3 by 1,
okay.
this is 3 by 1.
That makes sense, okay.
Okay? If you want to, now what is happening is we know this because we know this omega, we know I, and we know capOmega. Okay? How we need to know this. For rotation matrices, how do we, if you're, let me ask you this general question. If you know this, now how do you calculate R? You should, by matrix algebra, how do you calculate R?
You divide.
You don't divide, what do? You divide, but what is that called? Inverse.
Oh, inverse, yeah.
You take the inverse, right?
Yeah.
So if you were to do this, R inverse PQW,
you would get
ECI,
R dot.
R PQW, you would get identity because R inverse, let me write this down. R inverse PQW, ECI, R PQW, ECI, R ECI. So what I have done here is I have pre-multiplied both sides by the inverse of the matrix. What is this product?
That's all. Identity.
Identity matrix. This is a 3 by 3 identity matrix.
Wait, you say what?
Identity matrix. You know what an identity matrix is?
Yeah, when it's diagonal, it's equal
Yes.
on both sides.
So this is equal to R
Oh, because it's the reverse of it, so it's divided. Okay, yeah.
ECI. Okay. So if you multiply, you're going to just get this. You got this, right? Now you know this. It so happens for rotation matrices, R inverse is equal to R transpose. Okay, this is only true for rotation matrices. This is not true in general. R inverse and R transpose are different. R inverse, how do you take R inverse? How do you take the inverse of a matrix? You guys remember taking the inverse? The cofactor, and then you transpose the cofactor, you divide by the determinant. How do you take a transpose? You just change row to columns. Okay? So this is far more complicated than this. This operation is far more complicated than this.
But it's the same.
No, here it is the same. Only for rotation matrices it's the same. Inverse is a different operation, transpose is a different operation. Okay? So now, what is your...
That is not a question.
Huh?
Was that subscript for R? The R inverse equals the R lower?
This is the matrix, I'm talking about the matrices. R inverse is equal to R transpose. Okay? So if you look at this here, R transpose, you can write this as R transpose PQW into R PQW is equal to R ECI. can write this as R. Pay attention here. What I am doing is ECI PQW. I am changing the order. This matrix goes from PQW to ECI. This matrix goes from ECI to PQW. Okay. You get this R PQW equal to R. You got it? You just take a transpose of whatever matrix this is and multiply that by PQW. The R vector in PQW.
So you're going from R PQW to ECI. You multiply by ECI, the R of ECI. Well,
This you know how to take this one, right?
So we get that matrix.
And take the transpose. If you take the transpose of this, it becomes this.
it becomes ECI.
It becomes PQW to
That makes
ECI.
sense.
I thought
Here
that
it
was,
is,
I thought
the
that
way
was,
you read it is, you don't read it, that is a notation. It's ECI to PQW. So you go reverse.
we're in ECI, but we're going to
PQW.
I
If you
thought
take
we were in PQW when we did all of that. I thought we
If you take a transpose of this, you're in PQW, you're going to ECI.
Oh, okay. Yeah. Because you saying when we divided it, that was like taking a transfer inverse of that. So that's why we're going from ECI to PQW.
Here we are in ECI going to PQW.
Yeah.
Here we are in PQW going to ECI.
Yeah.
And these is just a transpose.
What's transpose mean?
Change the rows to columns, columns to rows.
What is it conceptually?
Huh?
Conceptually, what does that do?
It changes the configuration of a matrix. It changes the configuration of a matrix. It depends on how you see it.
Why are we transposing?
But we were trying to find R.
Pay attention. Why are we transposing? Let's tell you. Our goal here is try to focus on the goal. You're given the orbital element. Okay? You're required to find R and V in the ECI frame.
But you got it in the PQW.
Hang on. Let me explain. So please listen, everybody. You're required to find R and V in the ECI frame. Okay? From this element, there's a very easy relationship for R in PQW. Okay? R as seen in the orbit frame.
So we were given the orbital elements in the PQEW frame.
Orbital elements have the PQW frame in it. Got it? These elements, you see, try to correlate this and this. Right? If you are given this, you are given that matrix. Okay? Now, this R, there is a very simple relationship for R in the PQW frame, which is this cosine theta, sine theta, 0. Similarly for velocity. Once you get it in PQW frame, but you are being asked what is the vector in ECI frame. So how do you get the vector in ECI frame? You multiply, this is the relationship. If you have a vector in PQW frame, or if you have a vector in ECI frame, you multiply that by the rotation matrix, you get the vector in the PQW frame. Now what we need to know is, we need to figure out this. We have kind of found out this. These two are the same. So what we do is, if I pre-multiply this equation on both sides by the inverse of this, right? Inverse. This becomes inverse into its matrices, identity. Inverse into its identity, inverse into its matrices. A into A inverses. Huh? A into A inverse. What is A into A inverse?
One, identity.
Identity. What is B to B inverse?
A to A.
What is B to B inverse?
Well, identity.
Identity. What is C to C inverse? Huh? Identity. Everything is identity. A matrix multiplied by its inverse is identity. You know identity matrix, right? So matrix multiplied by its inverse or inverse multiplied by its matrix is identity. So when you identity, it's like multiplying by 1. Okay. So whatever entity you multiply with identity, that entity remains the same. So that's what it means. Now I'm so happy with this. The inverse is also equal to its transpose for a rotation matrix. Whether you take the inverse or transpose, you're going to get the same for this rotation matrix. You can do this in your, if you have calculators, if you have MATLAB, some other computing software. Construct a rotation matrix, take the inverse, take the transpose. You're going to get the same value. Not for every matrix. So that's the reason we say this is equal to that. Now this is expressed as, I change the notation. Any questions so far? Rotation matrix is now the context of rotation matrix here is, you know what ECI frame is. Now make sure you go through the lectures when you go back, okay? Because it's very important. It's like, let's say take that switch for example, okay? That switch. Take any point here. All right. Let's consider that switch, which is above your head there. Okay. The position of that. How do you identify the position of that? Huh? How do you identify the position? Now be serious. How do you identify the position? Where is that XYZ? Where is the origin? That cannot be the origin. If that is your this thing, if you identify the position of that, that cannot be the origin. Where is the origin?
You have to create a reference term.
You have to create your reference. You got it? How many origins can you create here? Infinite number, right? So it depends on where you're seeing it. Okay, so this could be one reference frame. This corner could be the origin. Okay, this would be the x-axis, y-axis, z-axis. Now that's somebody's reference frame. You can do it from there. You can do it from there. Now, if you see the same way, your orientation with respect to this frame is going to be different if I see it from there, right? But your orientation itself is same. You agree? If you're not changing your orientation, that position of that is not changing, right? It's there. But it depends on how you see it. Now, if you want to change the perception, the position or orientation of that with respect to this frame, that frame, we use rotation matrix. So this vector, think about this vector as something which you see in this reference frame. And this vector is something which you see in that reference frame. This transforms the coordinates. Got it? Now here it happens that ECI is earth frame, in the sense you're standing on the earth or in the core of the earth and seeing things. Got it? Your head is pointing this way and you're doing that. This, you're in the orbit. You're like practically sleeping in the orbit and then seeing how this thing rotates. This gives you the relationship, how you were in the earth and how you would change when you go into the orbit. That is a rotation. Make sense? A little bit? It's all about references. It's all relative, right? There's one more topic. I'll just quickly wrap this up.
Will there be matrices in the test?
Yes.
Okay. On linear compass and our geometry test?
Probably keep it. I don't know if you're going to really use it.
Okay.
It'll be mostly converting. So we do something called ground tracks. Now, do you understand ground tracks? Anybody? So when your satellite is, you realize satellite can have any orientation, right? Any configuration it can, not any orientation but any configuration. Your satellite, the orbit of a satellite. It can be, if you, if this is a rotation of the Earth, okay? The satellite could be this. What is the ground track of this if it's an equatorial
Same direction.
orbit?
Whatever's around the
Huh?
whatever's around the place.
It's actually will be the equator itself, right? The equatorial line. If it's an equatorial orbit, it will be a equatorial line. The ground track will be equatorial line. You agree?
I disagree because I don't know what you just said.
So you cannot disagree. If you say you don't know. So if this is your this thing. So this is the, let's say this is the equatorial plane, right? What is an equatorial orbit? Something which goes around the equator. Okay. If you look at the trace it makes, tracks it makes on ground.
So like the 2D.
The 2D view. You understand? So if you do a projection of that, now see, when you're on Earth, you have a limited view, right? That how is it going to pass over you? That ground track. If you understand the ground track of an aircraft?
Like the goal versus
No.
the rat.
Huh? So if let's say if I go from this point, okay, this point here. If I go like this, what is the track it is going to be?
But it's just short.
This line, right? If I do this,
It's this one.
it's going to do this point. If I do
Because
this,
because it's curving around the Earth, but when you just look at
When
it,
you
like
look
on
at
top,
it,
it's
Oh,
It's
the
just
trace
a
of
projection.
the projection of that on the Earth.
that's better.
Okay. So that is the ground track. You get it? Ground track is nothing more than transforming right ascension and declination in real time. What is right ascension?
it's coming out of line.
Always remember right ascension as
It's out of line. It's coming out of the line. Yes. It starts with the line.
so when you think about right ascension and declination, you have to think about latitude and longitude. You get it? Right ascension is
Longitude.
it's longitude. Right ascension is longitude. So your longitude runs from north to south. They're measured from east to west. Do you say 70-degree north longitude? How do you measure longitude? East to west, right? How do you measure latitude?
North and south.
North and south, right? North, but the lines run from east to west. Now think about at any position, can you figure this right ascension and declination is a latitude and longitude. That will reflect as a latitude and longitude, right? But in real time, this latitude and longitude is going to change.
Yeah.
Depending on how it's orbited. That is ground. You got it?
We're gonna look into it.
But conceptually, that is what a ground track is. Just look at, I would expect you to know conceptually on the definition of what a ground track is. Okay, because what is going to happen is, it's important because when I say, so we have been doing some tracking over here. Okay? The maximum elevation of any orbiting body, what could it be? You understand elevation? Elevation and azimuth? Azimuth, elevation? Both are angles. What is azimuth? Yes. Why is the elevation 90 degrees? How do you determine azimuth? So this is important for aircraft people as well.
The elevation's up.
What is the maximum elevation you're going to get? So you see, this is 90 degrees, right? Is it going to be always like this? Only when it goes exactly on top of you. That is when the elevation is 90. But it could go in front of you, right? If you're here, it could go in front of you. That time the elevation, maximum elevation could be, this is that elevation. It will be less than 90.
So still in reference to the ground tracks?
It is still in reference to the ground track.
So like we're talking about like what plane was over here, the elevation is different.
Yes.
It's at 90 when it's overhead.
There is a very direct relationship between elevation, azimuth, height, ascension, declination, and latitude and longitude. They're all similar. Got it? So your aircraft, if it goes like this, you're going to say the maximum elevation of the aircraft. The maximum, if you try to track the space station. Okay, you can easily track the space station if you just subscribe to their mailing list. They're going to tell you exactly when space station is above you, and you can actually see it. On a clear day, you can see the profile of a space station. If you have binoculars, you can very easily see it. During nights, you can see it as the brightest light in the sky. You can just, in fact, we just saw it a couple of days with the radio club. We actually tracked it and we could see it was orbiting. Okay, it is there's a very easy way to distinguish a satellite from an aircraft or from a star. Satellites don't blink. Okay, aircrafts are always blinking. Stars, they don't move as fast. What is it? How do you distinguish between star and planet? Twinkle. What twinkles? Stars twinkle and planets don't twinkle. So these days Mars is also visible. Have you guys observed Mars? It's this direction. If you observe during this is this thing, right?
How do you know that?
Huh? It will come up here. Not now, but you can see it as an orange light. So these are things you should do. This is what you should give you. So this elevation, azimuth, right ascension, declination, latitude, longitude, ground tracks. So these should not be. They should form the same. Attendance. Give me your attendance. Here. Right on this. Yes.
At Nicholas.
26.
Yes.
Your name,
So this should be negative sign, right?
Yeah, my